Chapter 4, Section 6, guys and gals, deals with the isosceles triangle. So we're going to deal with it today and some of the ramifications that come about from it. Make sure you know the proper spelling for isosceles. It's not one of the easiest words to spell. I myself have spelled it wrong numerous times on quizzes and tests to have students point it out to me. So do your best, folks. Isosceles. So there we are. So let's talk about parts of an isosceles triangle just to make certain that you understand what they're called. So if you see these names, you'll know. In an isosceles triangle, kind of like a right triangle, we have legs. So these, in this case, for an isosceles triangle, the legs are the two sides that are the same length because by definition, an isosceles triangle has two legs, or two sides, we'll say, of equal measure. And some people might say exactly two sides because that would rule out then the equilateral triangle. But for our purposes, we'll say for the moment that it has two sides that have equal measure, that's enough for us to say it's isosceles. So our legs, all right, are those two sides. The vertex angle, all right, this is the angle that the two legs create, all right? So the vertex, some folks will call it an apex, typically in three-dimensional things like cones, pyramids, that kind of thing. Vertex is typically used for the two-dimensional, in this case dealing with the isosceles triangle. The other two angles are known as base angles, and yes, these two angles should be the same, and we'll talk about that in a minute. But notice that is not part of the definition of what it means to be an isosceles triangle. To be an isosceles triangle only focuses on the leg measurements being the same. So two sides of equal measure there. Be aware, doesn't mention the base angles at all in the definition. We'll talk about this a little later on. And then that other side, that is a different amount. So remember, your leg measures have to be the same. This side more than likely will be different, though in the case of equilateral, it could be the same. We reference as the base. And again, it doesn't matter how we turn the triangle, that's still going to be referenced as the base. Though we could, for example, try to find the area of this triangle, and for that purpose, maybe draw a height here and let this leg be the base for the area formula. But again, just to note the terms. So let's talk about it. Some theorems that go along with being an isosceles triangle. This one is the one that most people screw up on just because it's a very simple, easy theorem, and we overlook a couple of things. So let me point it out to you. The isosceles triangle theorem states as follows. It says, look, if two sides of a triangle are congruent, in other words, it meets the definition of what it means to be isosceles, then the angles opposite those sides are, and here's the key word, congruent. All right, not equal, congruent. So if I know that triangle ABC is indeed isosceles with AC and BC being those two congruent sides, then the theorem states, wonderful, that means angle 1 and 2 here have to be congruent as well. And we could prove that pretty quickly, and we'll do so in a little bit. Take a look. The converse, in other words, if I were to take that and flip it on its head. So the converse of the isosceles triangle theorem states as follows. If two angles of a triangle are congruent, so in this case, if angles 1 and 2 are congruent, then opposite sides of those angles are congruent. So in this case, DE and DF. Notice congruent. All of this talks about things being congruent, not equal. Keep that in mind. Also, please do not ever reference 410 and 411. Don't do that in your work. I don't know why your textbook keeps doing that. Please don't do it. All right. Let's keep working with these. And then we'll start proving it. So here's a quick example. We've got points A, B, C, D creating two triangles here for us. Notice AB and AC are already denoted as being the same, and angle D and angle ACD are congruent to each other. So we need to name two unmarked congruent angles. Well, since these sides, AC and AB, are the same, then we'll call it angles 1 and 2 are also going to be the same. So I could say that angle 1 is congruent to angle 2. If you'd rather use the names that are already there, we could say that angle ACB is congruent to angle ABC. And that would work as well. Let's try another. It says name two unmarked congruent segments. Well, notice I've got D and C, and again, I'm going to erase this because these weren't part of the original markings. If I've got D and C being the same, then the converse of the isosceles triangle theorem tells me that the sides opposite these must also be equal. So in this case, I could say that segment AC is congruent. So AC is congruent to AD. All right, based on that isosceles, converse of the isosceles triangle theorem. And notice since those are the same and we've got markings, then obviously AB would also be congruent to them as well. But notice it wanted unmarked, and those two are already marked as being the same. So that's why we picked these two, because while one is marked, it's not marked relative to the other. Cool. So let's start proving this. So in this case, this is for the isosceles triangle theorem. We've got a triangle, in this case LMP, and we know that LM and LP are congruent. Remember, that's what it means to be isosceles, two sides having the same measure, same length. Cool. Here we go. We need to prove that M and P are indeed the same. So the first thing we did is let N be the midpoint of MP, and we can say that very simply. Every segment has exactly one midpoint. Cool. Notice our second statement is to draw the auxiliary line L and N. So we've drawn that in. No pun intended. So when we draw that in, we can say that exactly 2 points define a line. Cool, and that's how we can drop that in. Any 2 points, we get exactly one line. So at this conjecture, let's look. One way that we can prove that M and P are indeed the same is to start showing that these triangles, LMN and LPN, are indeed the same size. So we know we're given our triangle, and we know that LM and LP are the same. So let's go ahead and drop that information in next. So I'm just going to put quotations here for our given, and then we can just say, hey, that's given information. So cool. We went all the way to the third step before we threw in a given statement. Interesting. So now that we've got that in there, let's go on. So I know that LM and LP are congruent, so I'm going to go ahead and mark that. So I've got one side. Well, I also know that both of these two triangles, LMN and LPN, also share this side LN in common. So for my fourth statement, I'm going to say that LN is congruent to LN, because notice this triangle has it and this triangle has it, and we can say by the reflexive property. So I'm going to mark that. Cool. Well, all I need now is an angle or side to keep this ball rolling. I think it's going to be easier, since we've already got this midpoint scenario going on, that we can keep the ball rolling that way, because we've already shown these sides congruent. This side is obviously congruent to itself. I need MN and PN to be congruent to each other. And notice our midpoint is going to allow us to do that very, very nicely. So let's say that MN is congruent to PN, and we can do that by the midpoint theorem. So let's review. I've got these two sides, this side that's in common for both, and then finally these two sides. So I can say triangle LMN is congruent to triangle LPN by side, side, side. Notice side, side, side. Last but not least, our final step, the proof statement. So angle M is congruent to angle P, and we're going to reach for an old standby, C, P, C, T, C. Corresponding parts of congruent triangles are themselves congruent. So notice, since we proved the triangle is congruent, then that means those angles, by definition of what it means to be a congruent triangle, must be congruent as well. So again, there's a real quick, simple use of the theorem. Again, using that, we can then prove the theorem by saying, hey, we've got two congruent triangles. If these sides are the same, then cool, those angles have to be the same. So a nice quick proof of the triangle, and a nice quick proof to show, hey, how we could use CPCTC. It works for both. Some corollaries. We haven't seen corollaries in a while, that terminology. Remember, a corollary is simply a theorem that we bring about because of another. And we mentioned these earlier, that equilateral triangles and isosceles triangles are very, very closely related. So take a look. There are two equilateral triangle corollaries that we're going to use. Neither one of them is named. So please don't call it the equilateral triangle corollary because there's two of them. And please, please, please do not reference them by number. Please don't do that. So here's the first one. If a triangle, or excuse me, a triangle is equilateral, if and only if it is equiangular. So if I can show that all three angles are indeed the same, then that means all three sides are the same. And again, proving that is relatively straightforward. For example, let's draw a dotted line here for an altitude. If I know that A and C are the same, cool, then that means that AB and CB are the same. If I take and draw another altitude in and can show that B and C are the same, well then cool, that means those sides are the same. And what do you know? All three sides now match up. Cool, must be equilateral. Here's another one. Each angle of an equilateral triangle measures 60 degrees. So this one states, look, if I know all three sides are the same, well, then that automatically means all three angles are the same. And not only that, we know their measure, in this case, 60 degrees. So again, some interesting corollaries. And again, proving that would be, again, very simple. We could draw those altitudes similar to what we did here. We show that this is equal to this and that this is equal to this. Therefore, all three are equal. So that means I could have three of those angle measures, we'll call it x for now, all equaling 180. Again, using our triangle sum theorem, we know that to be true. We can divide the three on both sides and show that, yep, all the sides, or excuse me, all the angles rather, have to be 60 degrees. So again, pretty simple theorems to prove. But again, they are corollaries. They are direct results of what we've done with our isosceles triangles. So in our last example here, we'll get through it and then be done. We have to find the value of each variable. So we've got x and we've got y. So let's write that in. There's x and there's y. Notice in this case, I'm told that AB and AC are the same, which means that, cool, these angles have to be the same. And notice we already told it, so that means they're all the same. So congratulations, we have an equilateral triangle. So if I've got 2x, that means the angle itself has to be 60 degrees. We can divide by 2 and find that x is 30. So that was simple, 30 degrees. In terms of sides, well, we already know that the sides have to be the same because all three angles are the same. So that means 3 inches on this side has to be the same 3 inches on that side. So 3 inches on one side is equivalent to 4y subtract 5 on the other. Let's add 5 to both sides real quick. So that is 8 and 4y. We can divide by 4, and that means y is 2. All right. So pretty straightforward stuff today. Very practical, easy to use. But remember, some things that will trip people up. I see it every year. Make sure you know your vocabulary. Don't forget that. The isosceles triangle theorem, as well as its converse, deals in congruence, not equality. If you need to make that switch, you'll have to do it somewhere in your work, but that's not what the theorems say. Keep that in mind. Also, when it comes to proving the isosceles triangle theorem, it's a pretty straightforward proof. Again, we'll need a midpoint there on that base side with that altitude drawn in. Of course, we can draw that auxiliary line based on 2 points, define a line. And then it's just a little bit of work with our side postulate and then CP/CTC to show that, hey, if we've got two sides that are congruent, then those two opposite angles there also congruent. Because of all of our work in isosceles, we can then do some work with equilateral. We've got our corollaries there, so heads up on those. These are some that people forget, specifically later on in the year, so definitely keep those in mind. You might add them to your proof cheat sheet along with your isosceles triangle theorem, and then just make certain that you can use them in practical cases. All right. If you have any questions or concerns, bring them with you to class. Otherwise, have a good day.